Welcome, dear friends. I hope I'm audible to all of you. As stated during in your message on WhatsApp, I'm launching my first core question. Okay, and it's a very simple question, and I hope you have watched all the three videos which Professor Murukar has posted. Okay, and the plan of the lecture is to test you whether you have really internalized the concepts in the videos. Okay, so what my method would be, I would be taking few questions, and based on those questions I would schedule my lecture. That is, I would be speaking on that question so that you can connect to the videos, the concepts which I'm not sure whether you are really watched the videos. At least the responses, okay, the responses to this question, almost all of you have voted, and a very simple question it was, that in what is the reversible process. Okay, and of this, the responses is 60% of the students are saying that in the real engineering application, okay, the real engineering application, uh, reversible process is not possible. Okay, so the answer is So we'll find out what is actually happening. If your responses to a very simple question is that uh, uh, the real engineering application, the reversible process is possible. Okay, when you are saying that it is true, that is not correct. Okay, the answer is it is reversible process is imaginary process. Okay, and because it is an imaginary process, it is you cannot find any such process, no process in real life. Okay, no process in real life is reversible. So no process in real engineering life is possible. Please understand this. Okay, this has been made very clear in the video that a reversible process concept is a very useful concept, but it is fortunately unfortunately it is not possible to have a reversible process in real life. Okay, so let me share what is the result. uh, the result is, you see that 97% of the students have voted. Okay, and of which 40% of the students have not got this correct. Okay, so the answer is, in the real engineering applications, okay, we cannot have a reversible process. So having a reversible process in real engineering application, that is a false. Okay, that is false. Okay, 60% of the students have got it right. So understand this. So now whether the screen is visible. uh, Hello, am I audible? Can you see the screen? Pille ma'am, can you see the screen? Somebody can put this in the chat box, answer it. You cannot see. You can see the screen? Okay. Home party. You can start screen sharing. Pille ma'am, am I audible to you? Okay. Let me close the poll. Okay. Now can this? Yes. Yes. Okay. The screen is seen now. Vedant? No. Now it is seen. Okay. Thank you. Yes. Yes. Thank you, Gargi. Thank you, Vedant. Aniket, thank you. And now look at the screen. What is specifically mentioned here is a reversible process is an imaginary process. Okay, so no process in real engineering life is reversible. Okay, and then why is this concept important? This concept is important because as we go on discussing of ideal heat engine, okay, ideal heat engine or ideal thermodynamic cycle, namely a Carnot cycle, there this concept would be extremely useful, because without knowing what is a reversible process, you won't be able to appreciate the thermodynamic cycles which we are going to discuss in the future. Okay, so because we know that thermodynamics is basically about the heat engines or conversion of heat to work primarily, then we would be talking about the ideal heat engine, a Carnot engine, wherein this concept would be extremely useful. Not only that, but in many other thermodynamic cycles, where you know that thermodynamic cycle is basically you talk about a set of processes, thermodynamic processes, where you get back to the initial state. So a process, a real process, you need to differentiate between a real process and a reversible process. Okay, so the real process, for example, when you are talking about a power plant, okay, so in a power plant you talk about a boiler. So in the boiler, what happens is you are adding the heat to the working fluid. Okay, so this is a real process of heat addition. Or in the same power plant, you have a steam turbine. So in the steam turbine, what is happening is that the steam is expanding from a higher pressure to a lower pressure. Pressure. So that expansion is a real process. Okay, in the condenser, heat is rejected to the surrounding, right? So all these processes are real processes in your internal combustion engine. For example, in a petrol engine, right? You are talking about the heat transfer. We are burning the fuel in the engine, right? So there is a heat transfer. So this is a real process. So these real processes, we need to differentiate between the real processes and the reversible processes. Okay. So what makes the process reversible, and why is a process irreversible? So in the videos 1, 2, 3. This were dealt with what is a reversible process. That was the first video, right? And if you have understood that what is a reversible process, I want you to answer that in your chat box in the question column with your names. What is the reversible process? So put down these answers in your questions column, write your name and answer this question. Okay, the question is, what is a reversible process? Okay, so put down this answer now. I want you to answer in the chat box, sorry, not in the chat box, in the question column with your names. The question is clear. What is a reversible process? Okay. So let us see whether you have understood what is the reversible process. Okay, there is some query. All right. So can you put down the answers now? What is the reversible process? You type down the answers. What is the reversible process? I will read out few answers. Okay, so Sonone is saying that a process, reversible process, is a process which gets reversed. Okay, which can be reversed. In thermodynamics, a reversible process is a process whose direction can be returned to its original position by inducing infinitesimal changes. Okay, some property by its surroundings. Okay, process which, okay, Sanap. Okay, Sanap is there. Sanket Sanap has put an answer. Okay, so put down your answers. I would be looking into the answers after ending this lecture. Okay, because that would be captured by my GoToWebinar app. Okay, so whatever answers you are putting there, what is the reversible process? Okay, I would be capturing that, and that would help me understand which students, okay, are understanding the concept well, right? Now, in order to appreciate what is the reversible process, you need to appreciate one, what is a quasi-static process, and the second concept you need to understand is the concept of having having an nullifying effect on the surrounding. Okay, so the reversible processes, when you are talking about, okay, we said that these are the imaginary processes. There is no process in the real engineering life is reversible. Okay, but for making a process reversible, okay, we can imagine something. And what is that we imagine? So one thing which we imagine is the process has to be a quasi-static process. Okay, the process has to be a quasi-static process. If the process is not quasi-static, then it cannot be a reversible process. This is an important aspect in your concept of reversible and irreversible. Okay, so if you are appreciating this, I am just asking you one question, and I hope that you have put your answers to the question what is a reversible process in the question box, okay, which I would be seeing later, not here immediately. But let me put this question wherein I am asking you a very direct question, okay, whether the heat addition process in the petrol engine is a reversible process or not. Okay, uh, you have all seen, okay, you have all seen a petrol engine, and you are aware of what is a petrol engine. So I am taking a very practical kind of examples where I want you to appreciate the concept of reversibility by this concrete examples. Okay, so one concrete example is in the real engineering life is about the heat addition process in the petrol engine. You know that how is the heat addition process happening in the petrol engine? The heat addition process in the petrol engine happens via combustion phenomena. You know that petrol and air mixture is taken in the petrol engine, and then via spark plug there is a ignition phenomena, and because of ignition phenomena the combustion process happens in the petrol engine. Okay, so combustion process happens in the petrol engine. This process is a process of heat addition. Okay, there is a process of heat addition phenomena, right? So the working fluid, that is the ideal gas we can take, or you can take air petrol mixture. That air petrol mixture in the petrol engine takes in the heat. Okay, so that heat which is taken in the petrol engine, that comes because of combustion of the fuel. Okay, that is combustion of petrol. And because you know that it is a chemical reaction wherein energy is released, it's an exothermic reaction. Okay, so whether that kind of heat addition process in the petrol engine is a reversible process or whether it is an irreversible process, that is a question which is posed to you. Okay, so let me see what you are answering. Only 55% of the students have voted, and as I said that I would be henceforth taking your attendance not based on how many of you are registering for the course, but how many of you are uh, giving me the answers in the polls. Okay, that is an important parameter, because without that, without your involvement, it is futile to take and engage lectures, right? So it's a very simple question. Try to understand this. The question is, what happens whether the process of heat transfer, okay, is reversible or not when you're talking about a petrol engine. So the answer is the process is okay. Almost 85% of the students have voted. So let me close the poll and share the result. The answer is the heat addition process in the petrol engine is irreversible. Okay, so it is not reversible. So the answer is no and not yes. Okay, so 27% of the students have got it wrong. 73% now understand that the heat addition process in a petrol engine is not a reversible process. Okay, is not a reversible process. Let me hide this and let me put another question. Okay. So when you are talking about a reversible process, okay, as was explained, there are two things we need to keep in mind. Okay, I've seen your answers in the questions column which you have said. So one or few students are answering it correctly. So when you are talking about a reversible process, please note that when you are talking about a reversible process, okay, can you see the screen now? Yes, can you see the screen? Put something in the chat in your thing. Screen is seen? Yes, okay. So look at this screen. What the question? What is a reversible process? When you are talking about a reversible process, there are two things. Okay, as the name indicates, we need to get back to the original state. You know that in a thermodynamic process, when you are talking about a thermodynamic process, okay, the system is moving from some state 1 to state 2. Okay, so a system moves from some initial state 1 to state 2. Okay, and when you are talking about a reversible process, so one of the thing is that we should get back to the state 1. Okay, so it can be reversed, it should be reversed. Okay, so the process should be reversed. We should be in a position to reverse this process. Okay, hence it is a reversible process. So that is not a very intelligent idea. Okay, so what is the important parameter is the important parameter of reversible process is that it should be reversed without any trace on the surroundings. Okay, or there should be no trace left either on the system or on the surroundings. Okay, so this was well explained in the video, but I will just repeat it in a brief manner. That when you are talking about a process, when you are talking about a process to happen, so the real process happens if there is an inequilibrium. Okay, a real process would happen only if there is an inequilibrium. Okay, this concept you have learned, right? So the inequilibrium could be because of temperature difference, and then it is called as a temperature thermal inequilibrium, or uh, the inequilibrium could be because of the pressure difference. It could be a mechanical inequilibrium, or the inequilibrium could be because of the change in the chemical composition, and that is called as a chemical inequilibrium. Okay, so whenever we are talking about any process, a real process, the real process happens only if there is an inequilibrium. Now when you are talking about an ideal process, a reversible process, then what we are saying is that this process has to move extremely slowly. Okay, so this, if you take this process 1 to 2, then what we need to do is that we need to divide this process into infinite number of states. Okay, infinite number of states, infinite. Okay, I am saying infinite number of states, that is uncountable number of states, and all these states between 1 and 2, all the states between 1 and 2, they would be in thermodynamic equilibrium. They would be in thermodynamic equilibrium. And if that happens, that is, for example, an example was given to you about an expansion process. We are talking about an expansion process. Okay, and if this gas has to expand, okay, and if this pressure is, let us say, 1 bar, this pressure is 1 bar, and let us say if this pressure, okay, if this pressure is 0.9999, and this 9 you have to write, up to infinity, right? So it means that this delta p is infinitesimally small. It is very, very small. Okay, It is extremely small. Okay. So small that we cannot just uh, get the difference between the two. Okay, so that difference in the pressure, for example, when you are talking about expansion process, is infinitesimally small, then that process we can say, okay, that process of expansion we can say that it is, if that expansion would, let us say, is infinitesimally small, is driven by infinitesimally small pressure difference, and it is a quasi-static expansion. It is a quasi-static expansion. That is, the process has to move to a new state, and that difference is very small. So the process would be slowly move to a new state. Let us say 1 dash, 1 dash. Okay. So if you go on doing this, if you go on having this kind of delta p, which is very very small always, then and if you proceed to some new state 2, proceed to new state 2, okay, and that kind of expansion, if you uh, calculate that work on a pressure volume diagram would be, if it is a closed system, it would be given by the area under 1 to 2, area under 1 to 2. Okay, so this process moving from 1 to 2, 1 to 2 in such a manner that this process moves very slowly. This process moves very slowly, that is, it is quasi-static process, and it goes to a state 2 without any dissipation, without any friction. It moves extremely slowly without any friction from 1 to 2, and the, let us say, the work done is W. The work done is W, right? It is an expansion work. It is an expansion work. And if you want to come back, what I was, let us talk. This is 1 and this is 2. Okay, now it would be expansion work, right? The volume is increasing. So if you are moving from 1 to 2, if you are moving from 1 to 2, from a higher pressure to a lower pressure, that is an expansion work, and in such a manner that all the states between 1 and 2 are in thermodynamic equilibrium, rather near thermodynamic equilibrium, and the process is a quasi-static process. It moves extremely slowly such that all the intermediate states are in thermodynamic equilibrium, and there is no dissipation, there is no friction, and there is no friction, then we can get back again from 2 to 1. We can get back again from 2 to 1, okay, without any trace on the surrounding, because this work would then be nullified. That work would be nullified. You would be getting the same work. Hence, if you go from 1 to 2 quasi-statically and without any friction, you would be getting work 1 to 2, right? And if you want to get back from 2 to 1, that is, let us say this is the movement. Okay, so this is the initial state 1 and this is the final state 2. This is the initial volume V1 and this is the final volume V2, and you are moving from volume V1 to V2, okay, such that the delta P is always negligibly small. Delta P is always negligibly small. That means that you need to move from 1 to 2 extremely slowly. And let us say that in this phenomena there is no friction, then while you move quasi-statically from 1 to 2 without any friction, you would get certain work W. Okay, there would be certain work W1 to 2, right? Now if you want to get this gas back to the state 1, if you want to get this gas back to the state 1, back to the pressure P1, then you need to do a compression work on the system. Okay, you need to do a compression work on the system, and you will find that that compression work W2 to 1 would be equal to W1 to 2, because there is no dissipation and the process is quasi-static, and hence there is no stress left on the surrounding or within the system. There is no stress left on the surrounding, there is no stress left within the system. Okay, so this way we are talking about getting back to the initial state, but getting back to the initial state is not enough. We need to get back to the initial state without leaving any trace on the system and the surrounding. So the complete answer, what is a reversible process, is it's not simply that the process is reversed. It can be reversed and we can get back to the initial state, but the complete answer is the process can be reversed. We can get back to the initial state without leaving any trace, either on the system or on the surrounding, either on the system or on the surrounding. Okay, so two things are important for the process to be reversible. We need to have equilibrium, near equilibrium. As the process proceeds, the process has to go through near equilibrium states, that is almost equilibrium states. And second thing is that there has to be no dissipation, so that there is no trace left behind after the initial state is regained, after the process is the initial state is obtained, the process is reversed. There has to be no trace left within the system and the surrounding. I hope this concept which was explained to you in the video 1 is clear. Okay, and let me ask you a few questions again. So the question is, can we say that if there is a process of can we say that if there is a process of expansion in the steam turbine, okay, then because of the friction, the process becomes irreversible. Okay, so 70% of the students are answering it correctly. Okay, the reason is simple, that because we are talking about friction. Okay, so friction would lead to dissipation of energy, and hence there would be some traces left on the surrounding, some traces left on the surrounding. So we can reverse the process. We can obviously reverse the process when you are talking about expansion from a state 1 to state 2. However, because you are having certain frictional losses, okay, so that would leave certain trace on the surrounding when you get back to the state 1. Okay, so when you get back to the state 1, you will not be getting exactly the nullifying effect on the surroundings. Okay, that I would be explaining you in short. Okay, so the answer is, let me close the poll and show you the result. The answer is, can we say that because of friction the process is irreversible? So the answer is yes. 70% of the students are saying it is yes. And please note that in spite of the fact that the process is quasi-static expansion, the reason is, we are talking about a quasi-static expansion, but we are talking about some losses because of friction. Okay, so when you imagine, now if you look at this, let me show you the screen. I hope the screen is visible to you. Okay, so if you look at the screen, I had drawn a steam turbine. Okay, I had drawn a steam turbine, and we are talking about an expansion. Okay, an expansion. So an expansion process, let us say, proceeds from a state 1 to state 2, and it means that you are expanding the steam from higher pressure P1 to a lower pressure P2, and you are expanding it quasi-statically. It means that you are proceeding very slowly. The process is extremely slow. Okay, and when you are proceeding from a state 1 to state 2, when you are expanding that steam from a state 1 to state 2 extremely slowly, however, because there is some friction. So what would happen is that when you are getting an expansion from 1 to 2, because this is a steam turbine and steam turbine is a power producing device, so you get certain work which is W12. You would get certain work which is W12. And when the system moves from a state 1 to state 2, you are getting certain work output from the steam turbine, right? Now, if you want to get back to the state 1, okay, if you want to get back to the state 1, it means that you need to supply certain work from W2 to 1. Okay, without that means this is an expansion work, so you need to do this is an expansion work. It means that there is a work done by the system on the surrounding. Now if you want to get back to the state 1, you need to do the work. If you need to do the work by the surrounding on the system, so you need to do the work on the system. Now earlier it was the work done by the system, now you need to do the work on the system such that you get back to the state 1. Okay, so you can get back to the state 1. Okay, you can get back to the state 1, and you can proceed very slowly also. You can proceed very slowly also, quasi-statically. However, because certain energy has been lost, dissipated, because of friction, because this is a mechanical system, you know that steam turbine would have blades on it, right? Blades on it, and these blades would rotate the turbine proper. It would rotate the shaft, and the shaft work is what is obtained, right? So because this is a mechanical system, there has to be certain friction, and this friction would lead to certain dissipation of energy. So now if you want to get back to the initial state, what it means is that you need to do some extra work. So this W21, if you want to get back to the initial state 1, you need to do W21 which is not equal to W12. It means that certain traces on the surrounding is left. Okay, you are you are you are not getting back to the state 1 without leaving traces on the surrounding, right? So if you are leaving traces on the surrounding, and why there are traces on the surrounding, because this work supplied and work produced is not the same, right? So work produced when you are getting from 1 to 2 is not the same as the work required for getting back to the state 1. So the process is reversed, right? But there is dissipation, and let me go to the next process. Okay, and we are talking about a reversible process. Okay. This question is designed to confuse you a bit. Question is, we are talking about a steam turbine of the power plant. Okay, as the schematic was drawn to you. Okay, and the question is, if the steam turbine of the power plant is insulated, okay, there is no heat loss. Okay, so the quasi-static expansion is reversible. Okay, you are insulating the steam turbine, right? You are insulating the steam turbine, and I am asking you that when you are having an expansion, of the steam in the steam turbine, in that process is a quasi-static expansion. Okay, we want to imagine it. Okay, it is a quasi-static expansion. Then whether that process of expansion is reversible or it is not, right? So again, note that I have not mentioned that it is a frictionless expansion. I have not mentioned that it is a frictionless expansion. What I have mentioned is that the power plant is the steam turbine is okay. So we need to understand that though the steam turbine is insulated, it won't have any bearing on the frictional losses. It won't have any bearing on the frictional losses. So the frictional losses, the motion which is there in the steam turbine, which is going to cause the losses, the dissipation, that would make the process irreversible. Okay. So even if you are insulating the steam turbine, and uh, because it is a mechanical system, there would be certain friction. And if you are not imagining that the steam turbine is a frictionless kind of steam turbine, then that process of expansion, if you are not imagining that the steam turbine is a insulated steam turbine, then that process of expansion would remain irreversible. It won't be reversible. Please note that even if you are insulating the steam turbine, and if there is a actual steam turbine, because in most of the power plant, if you go and see, okay, you'll find that physically, if you see the steam turbine, you'll find that the steam turbine is insulated. Okay, and insulation has to do with the heat losses. So by insulating the steam turbine, what we are doing is that we are making sure that there is no heat loss, but we are not making sure that there is no friction, right? So there would be friction, and because there is a friction, the process would be irreversible. Okay, there is a dissipation, and hence the process would be irreversible. Are you getting the point? So the answer is 80% of the students are voted. Okay, and of which 60% of the students have got it right. Okay, please note that though the process there is an adiabatic process because it's insulated, right? So the process would be an adiabatic process. There would be no heat loss, no heat exchange between the system and the surrounding, but still there would be dissipation, and this dissipation should lead us to say that the process is an irreversible process, right? So understand this very clearly, that when you are talking about an expansion process which has certain friction, then it is to be a irreversible process. Without friction, yes, and with the process being quasi-static, the process would be a reversible process. Okay, so 60% of the students have got it right. Okay, and let me go to the next part. And again, this has to do with the steam turbine thing. Okay, steam turbine, you would find a very common kind of application is that in your engineering, right? All your power plants would have a steam turbine, and when you go to the higher studies, okay, when you do mathematical modeling of power plant to analyze the performance of the power plant, this understanding would be very crucial. Okay, that what kind of process happens in the steam turbine, what kind of assumption we need to take for what is happening in the steam turbine, what kind of process we should imagine for the steam turbine. Okay, that has to be clearly appreciated. Okay, now this is a very obvious question after this discussion. If you are attentive enough and if you are listen to what I am speaking continuously, what I am repeating continuously, I guess that you should be in a position to answer it. Okay, those who are not able to answer this, they are either not attentive or they have not listened to the videos, and they are also not able to internalize this concept. Okay, this is very obvious question after so much discussion. Okay, we need to be very clear that what the answer is. Okay, so what is the question? The question is, we are talking about the steam turbine, and what kind of steam turbine we are talking about? We are talking about insulated steam turbine. Why is that we are talking about insulated steam turbine? Because in the question it is given that it is having no heat loss. Okay, there is no heat loss. So when there is no heat loss, okay, it's an insulated steam turbine. And what kind of expansion we are having? So we are having an expansion which is a quasi-static expansion. It's a quasi-static expansion. It means that as the steam expands from a higher pressure to a lower pressure, all the intermediate states of expansion can be assumed to be the states wherein the system is in thermodynamic equilibrium. Okay, all the intermediate states are in near thermodynamic equilibrium, as a result of which the process of expansion, okay, because it's mentioned in the question that it is a quasi-static expansion process. Okay, and one more thing is that we are talking about a frictionless steam turbine, that in spite of the fact that it is a mechanical system which is undergoing a motion, okay, we would say that it's a frictionless case. There is no friction, there is no dissipation of the energy, and that energy is not converted to internal energy, and hence there is no loss, and hence the process is a reversible process. So the answer is very obvious, and still I'm surprised that 30% of the students are getting it wrong. Okay, so the correct answer is, and we are talking about expansion phenomena in the steam turbine where there is no friction, the process is quasi-static, and there is no heat loss. So obviously, in absence of any inequilibrium, in absence of any inequilibrium, in absence of any dissipative effect, the process has to be a reversible process. A process has to be a reversible process. So of the students who are quoted, 70% of the students have got it right. Okay, 75% of the students have got it right. Okay, so the answer is, let me share the result. The answer is yes, it is a reversible process. Yes, it is a reversible process. When you are talking about an expansion phenomena in a steam turbine which is frictionless, quasi-static, then it has to be a reversible process. Okay, let me move on to the next concept, and this concept has to do with your understanding of the third video which was explained to you about the process of heat addition being reversible or irreversible. Okay, so let me put this question in a slightly different manner. Okay, I'm launching this question, and let us see now what. In the third video, you have been explained what do you understand by reversible heat transfer. Okay, so if you have understood this concept of reversible heat transfer, then I hope that you would get this answer correct. Okay, and it appears to me from your responses that you have not understood the concept of reversible heat transfer. Let me explain you what is a reversible heat transfer after you answer the polls. Okay, so because the responses are not very encouraging, the question was if the temperature is 1000 Kelvin and the working fluid is at 800 Kelvin, there is no heat loss. Whether the heat transfer is reversible. 60% of the students are saying that it is reversible, which is wrong. Okay, I am short of time, but I simply say that the process is irreversible. I would explain this in the next lecture, but I want you to get back to the videos, okay, because you are getting this answer wrong. The correct answer is it is false. Okay, why it is false, we will be explaining it in more detail in the next class. But I want you to please watch the video if you want to understand the concept of reversible heat transfer. Okay, so with this, I would close. The answer is false. Okay, and why is that false? That I would explain you in the next class. Okay, thank you for joining. Thanks a lot, and please listen to the videos again so that your concepts are right. Okay, so I'm